In the last lecture, we have started with the linear algebra. We have seen that how to define a matrix, how to define the determinant, and then we have started with the basic thing that what is going to be the latent root, and then we have defined the latent vector also. Okay, so now we need to understand how this latent roots or eigenvalues are related to the matrix, and what are the properties that eigenvalues has. Okay, so that we need to see all. Again, so I hope you are able to see this Jamboard. Are you able to
Sir,
see
can
this?
you share the Jamboard?
Yeah, I have shared already. It is in chat box. You can join. Okay, so are you able to see this Jamboard now?
Yes, sir.
Yes,
Yeah.
sir.
Okay, that's great. Okay, so we have defined the eigenvalues and eigenvectors, and now we need to understand what are the different properties of eigenvalue. Okay, so I hope you are writing with me. Okay, so please do write with me. Okay, and try to solve the examples with me. Okay, so first thing that we need to understand, suppose we have a matrix. Okay, so what we'll be having, let A be a square matrix with lambda i's, I running from 1 to n. Okay, let A be a square matrix with lambda i's as eigenvalues, again, of A. Then what we'll be having, we need to understand what is the sum of all eigenvalues. So then sum of all eigenvalues equal to sum of all diagonal elements of A. Okay, so what do you have? That is, if I consider summation I running from 1 to n lambda I, then it is nothing but summation I running from 1 to n aii. Okay, because aii will be the diagonal element. Like you can see, this will be a11, a22, a33, and so on. The last diagonal element will be an. Okay, so if I consider the sum of these elements a11, a22, a33, then it is nothing but the sum of the all eigen values. Okay, so we can have, without calculating the eigenvalues, we are able to calculate the sum of the eigenvalues. Okay, so for example, you can have, let A is equal to 231, 305, 109, 129. Okay, suppose this is the matrix. Okay, then the sum of eigenvalues of A is. So can you tell me what will be the sum of the eigenvalues? What do you
11.
have here? We have, this is the diagonal element, this is the diagonal element, and this is the diagonal element. So what this property says, this property says that the sum of all eigenvalues is equal to sum of all diagonal elements. Okay, and these are the diagonal elements here. So can you tell me what will be the sum of the all eigenvalues of this matrix A? What will be the sum? Anushri, can you
11.
tell me?
11.
Yeah, yes. So it is going to be 11 because we have 2 plus 0 plus 9. So we have the sum of the diagonal values is diagonal elements is going to be 11, and hence we can say the sum of the eigenvalues is going to be 11. Okay. So now we talk about the sum. What about the product? Yeah. So what we can say about the product of the eigenvalues? Yeah. So
18.
what is happening? Let A be the matrix of order n. So when I say only one element, that means this is the square matrix with the same number of rows and columns. Then what you can say is the sum of, now we want to think of the product. Okay, so we have seen the sum. So the product of all eigenvalues of A is equal to, okay, is equal to determinant of A. Okay, so that's why we wanted to know about the determinant. So that is what we can say is let lambda i's be the eigenvalues of matrix A. Then what you can have is product. Okay, so how we denote the product? The product is denoted by pi. Okay, so the product is denoted by pi. So this I is running from 1 to n. So product of all lambda i's equal to determinant of A. Yeah, so for example, you can have let A is equal to 1 minus 1 2, 0 2 minus 1, 0 0 4. Okay, then the product of all eigenvalues of A is. So can you tell me what will be the product of all eigenvalues?
8.
Have you calculated the determinant?
Yes, sir, it's 8.
It is going to be 8. So 8. Okay, that is what we have. Determinant of A is equal to 8 is equal to the product. Now this is 3 by 3 matrix, so I will be running from 1 to 3, and you will be having lambda I. Okay, so or you will be having lambda 1 into lambda 2 into lambda 3, and that's going to be 8, which is determinant of A. So this way you can have the product of the all eigenvalues is going to be the determinant value of the matrix. Okay, so now we got the sum, we got the product. Okay, now next we need to think of what about the relation of the eigenvalue of A and the matrices derived from A. Okay, so the matrices which can be derived from A will be, if I know A and A inverse exists, then we can find A inverse. But we know that if I want to find out A inverse, then I have to find out adjoint of A. Okay, then only I am able to get A inverse. We know the relation between the A inverse. So what is the relation between A inverse? So A inverse is equal to 1 upon determinant of A into adjoint of A. Okay, so this is how we find the inverse, provided that the determinant of A is not equal to 0. Okay, so if this determinant not equal to 0, then we can find out the inverse using this formula. Okay, so that means I am able to derive A inverse from A if it exists, provided that it exists. Okay, then what is the relation between the eigenvalue of A and eigenvalues of A inverse? Okay, so we can have, if lambda is eigenvalue of A, then okay, we need to think of is eigenvalue of A inverse. Okay, so we have to find out what will be the eigenvalue of A inverse. We know the eigenvalue satisfies an equation AX. Okay, AX is equal to lambda x. Okay, where x is going to be the eigenvector. Now multiply this here. A is a matrix and lambda is going to be the scalar. So what we can do is we can multiply this by A inverse. So suppose we multiply by A inverse, and then you will be having this is A inverse into lambda x. Okay, so that's what we will be having. Now this A inverse into A inverse into A and to x, and this lambda is being a scalar. I can write this as A inverse into x. Okay, because this A inverse is a matrix, S is a matrix, so we can write these two matrices, and this being a scalar, we can have it. So can you tell me what is the value of A inverse into A? I. So I, or it is identity, and this is going to be x, and you'll be having lambda times we have A inverse x. Okay, now think of this lambda being a scalar, so I can take this scalar on the other hand side, and I can write A inverse x is equal to 1 upon lambda times x. Is that okay? Are you getting this? So I have taken this lambda on the other hand side. I into x is going to be x only. Correct?
Yes, sir.
Okay, so now see, if I know that x is going to be the eigenvector, then my lambda is going to be the eigenvalue. Okay, so if any vector is operated by the matrix and it is generating the scalar multiple of that vector, then this scalar is also called as eigenvalue, okay, of the given matrix. So here you can see this is a matrix. A is a matrix, so obviously A inverse is a matrix. So A inverse is operated on this vector, but it is generating just a scalar multiple of this vector. This vector is not changing. So this vector remains same, but the action of this matrix A gives the scalar multiple of this vector, and that's why this is going to be the eigenvalue of this matrix. So we can say 1 upon lambda is the eigenvalue of the matrix A inverse. So are you able to get that?
Yes, sir.
Are you getting this? Yeah.
Yes, sir.
That's why I have kept this. So compare this statement and this statement, so you can understand if lambda is eigenvalue of A, then this 1 upon lambda becomes eigenvalue of A inverse. Okay, so easily we are able to get the eigenvalue of A inverse. It is just the reciprocal of the eigenvalue of A. So if I know the eigenvalue of A, then we are able to find the eigenvalue of A inverse easily. And what is that easiest way? By finding the reciprocal of the eigenvalue of A. So now next we think, okay, if lambda is eigenvalue of A, okay, then I need to find the eigenvalue of adjoint of A. Okay, then is the eigenvalue of adjoint of A. Okay, so again we know the relation. So what is the relation we know? A inverse is equal to 1 upon determinant of A into adjoint of A. Correct? So this is the relation. Is that okay? Are you familiar with this relation?
Yes, sir.
Yeah.
Yes, sir.
Okay. So I will operate this on the vector. Okay. I'll operate this A inverse on the vector. So suppose we operate this on the vector. So I'll be having A inverse X, and then this is the same matrix. So I'll operate on X. But what I know is, since I know that A inverse X is nothing but 1 upon lambda times X, that we proved in the previous comment, no? Okay, so I can write this as what this is going to be. This is going to be 1 by lambda times X, and this is equal to this 1 upon determinant of A is going to be a scalar. Okay, so this is a scalar value. I can write this as 1 upon determinant of A, and this is adjoint of A operated on X. Okay, so this being a scalar, can I write it like this? Determinant of A upon lambda, because determinant of A is also a scalar value. Lambda is also a scalar value operated on X, which is same as adjoint of A operated on X. So can you guess what will be the eigenvalue of this matrix? What will be the
Determinant A
eigenvalue of
upon
adjoint of A?
lambda.
Yes, determinant of A upon lambda. Okay. So here we got the action of this matrix and this scalar is going to be same on the vector, and that's why this determinant of A upon lambda. Okay. So determinant of A upon lambda is the eigenvalue of adjoint of A. Yeah, so this easily we are able to prove this if we know the basic relations on matrices. Okay, so we got this here. Yeah, that the eigenvalue of this adjoint of A is equal to determinant of A upon lambda. Okay, now suppose if lambda is eigenvalue of A, then I want to find the eigenvalue is the eigenvalue of A raised to n. Suppose we want to find the eigenvalue of A raised to n. So what we know is, we know that Ax is equal to lambda x. Okay, as per the definition of the eigenvalue and eigenvector, that Ax is equal to lambda x. Let us multiply this Ax by A. So we can multiply this, and then now this will be A square operated on x, and this will be lambda is a scalar, so we can have Ax. But what is Ax? Ax is again lambda x. Okay, Ax is equal to lambda x, no? So what we got here? We got lambda square x. So I got A square x is nothing but lambda square x. Now multiply this again by A. So we can have, okay, so we can have A into A square x is equal to A into lambda square x. Again we can have this A cube x. Okay, and now this will be lambda square Ax, but what we know is lambda square Ax is lambda x. So we got here lambda cube x. So we got here A cube operated on x is nothing but lambda cube x. Okay, so what will happen if I again multiply this? I'll be having A raised to 4x is equal to lambda raised to 4x. Okay, then I'll be having again multiply A raised to 5x is equal to lambda raised to 5x. Okay, again multiply A raised to 6x is equal to lambda raised to 6x. Can you identify the pattern? Square here,
Raised to n plus
here,
1.
cube here, fourth power, fifth power, sixth power. So what you can say, a raised to n x is equal to lambda raised to what?
Lambda raised to n.
Lambda raised to n.
Yes. Okay, that's correct. Okay, so what we got is we got lambda raised to n. That means the eigenvalue of a raised to n will be, what will be the eigenvalue of a raised to n?
Lambda raised to
Lambda
n.
raised to n.
Correct. Okay, so it will be lambda raised to n. So we got here the value, if lambda is eigenvalue of a, then lambda raised to n is a eigenvalue of a raised to n. Okay. And now if there is a polynomial, okay, so suppose there is a polynomial or there is a function of a, okay, so we can have 6. Okay, if lambda is eigenvalue of a, then is the eigenvalue of f of a, the function of a. Now see, we can think of, suppose we have a function of a. Okay, so simple function we'll consider f of a. Okay, then the eigenvalue of a is going to be lambda only. Okay, so what do you have? And the eigenvalue of a is going to be lambda. Correct. Now suppose f of a is equal to a square plus a. Okay, then what is the eigenvalue of a square? Can you tell me the eigenvalue of a square?
Lambda square.
Lambda square. Yes. What is the eigenvalue of lambda a?
Lambda.
Lambda. So can I write this as if it is f of lambda?
Yes.
Because f of a is a square plus a, no? And I am getting a polynomial in terms of lambda. So lambda square plus lambda. So that can I write it f of lambda?
Yes, sir.
Yes. Okay. So suppose f of a is a cube plus a square plus a. Then what is the eigenvalue of a cube?
Lambda cube.
Lambda cube, right. Okay. What will be the eigenvalue of lambda square?
Lambda
Sorry,
square.
a square. It is going to be lambda square, and then it is going to be
Plus
lambda.
lambda.
Again, it is going to be f of lambda because my f of a is this, so this will be f of lambda. Okay. So what it means, f of a has the eigenvalue f of lambda. What it means, f of a has the eigenvalue f of lambda, and that's what we have here. So if lambda is eigenvalue of a, then f of lambda is eigenvalue of f of a. So it is eigenvalue of f of a. Okay. Now we think of the next. Okay. So suppose we have the next. Okay. So let A, B or triangular matrix. So either it may be a upper triangular matrix or it may be a lower triangular matrix. Okay. Then what will be having? Okay. Then the diagonal elements of A are the eigenvalues of A. So what do you have? A may be a triangular matrix, so it may be upper triangular matrix or it may be a lower triangular matrix. So the eigenvalues of A are nothing but the diagonal elements. Okay, so for example, we have let A is equal to 1 0 2 0 minus 2 3 0 0 minus 1. Okay, what kind of matrix is it? Is it a lower triangular matrix or upper triangular matrix?
Upper.
Upper.
It is the upper triangular matrix. Okay, so B, a matrix of order 3 by 3, correct? Okay, and this is being a upper triangular matrix, so our requirement is only a triangular matrix. So if I have a triangular matrix, then it is sufficient. Okay, whether it may be a upper triangular matrix or it may be a lower triangular matrix, so this is going to be sufficient. Okay, so this is a upper triangular matrix, and hence, can you tell me, hence the eigenvalues of A are, so what will be the eigenvalues? 1, minus 2 and minus 1. Okay, because these are the diagonal elements. Okay, so this way we are able to get the eigenvalues of the triangular matrix, whether it is upper triangular or it is going to be the lower triangular. So suppose we consider another example. So we can have like B is equal to minus 2 0 1, okay, 0 minus 1 3 and 0 0 3. Okay, so this is a matrix. Okay, B, the matrix of order 3 by 3. Okay. Then what type of matrix is this?
Upper triangular matrix.
Upper triangular matrix, correct. So this is upper triangular matrix. What will be the eigenvalues?
minus 2 minus 1 3.
Minus 2 minus 1 3. Okay, then we can say the eigenvalues of B are minus 2 minus 1 and 3. So same thing you can do with the lower triangular matrix also. Okay, so this way we got the eigenvalues of the triangular matrix. Now can you tell me what will be the eigenvalues of the eigenvalues of identity matrix R? So can you tell me what will be the eigenvalues of identity matrix?
1 1
1 1 1.
Correct. R equal to 1. Okay. So the identity matrix, whatever the order of the identity, that many eigenvalues the identity matrix will have, and all the eigenvalues will be equal to 1. Okay. So this is the only matrix which having the all eigenvalues 1. Yeah. So it is going to be the identity matrix. So see here what we have seen up to 8. The sum of the eigenvalues is going to be sum of the diagonal elements. Product of the eigenvalues is going to be the determinant of A. So if lambda is eigenvalue of A, then 1 upon lambda is eigenvalue of A inverse. Determinant of A upon lambda is the eigenvalue of adjoint of A. Then lambda raised to n is the eigenvalue of A raised to n. F of lambda is the eigenvalue of f of A. Then we have the triangular matrix with the eigenvalues situated at the diagonal places. So diagonal elements are the eigenvalues of the triangular matrix. Then we have the eigenvalues of the identity matrix are equal to 1. Okay. So now these are the simple relations, okay, of the eigenvalues and the matrix. Okay. Now we need to think of eigenvector. Okay, so what you have observed when we have proved this all relations? So what was your observation? So what was
All the
your
operation are done on scalar.
what was your observation? What you have observed about the eigenvectors? We have proved that the several matrices has the several eigenvalues, okay, or the different matrices has the different eigenvalues. So we proved that using the relation, the simple relation that Ax is equal to lambda x. So what happened to x? What was the change in x? Tejas Vandarkar,
What, sir?
Tejas,
Yes, sir.
yeah. So we have proved this many relations using a basic relation, the definition of eigenvector. Okay. So what are the changes that you have observed in the eigenvector corresponding to lambda? Nehanshu, what is the change that you have observed? Prachiti,
Sir, I did not understand. Can you repeat?
yes. See, we have proved near about 8 properties for eigenvalues, correct? Have
Yes,
you got 8 properties? Correct. Now, to prove this all, I have used only one relation, Ax is equal to lambda x, correct?
Yeah, sir.
Yeah. So we observed the different changes in matrices and in their eigenvalues. Okay. So my question is, what are the changes that all you have observed in eigenvector x? So what happened to x? What were the changes that you have observed?
In all the operation x is same. Did it change?
Yes, in all the operations, x remains as it was. Okay, so what it means? It means that the eigenvector which is corresponding to lambda is same as the eigenvector corresponding to 1 upon lambda is same as the eigenvector corresponding to lambda raised to n is same as the eigenvector.
So basically x is constant. It does not
No,
change.
x is not a constant.
No, it changes, but
Eigenvectors remains same. Okay, so when you say constant and remains same, they are two different things.
yes, sir.
Okay.
Yes, sir.
Okay, so it doesn't change. Okay, but it is not a constant. Okay, it doesn't
Yes,
change.
sir. It remains same, right?
Yes, it remains same. Okay, so that means if I can find out the eigenvector of A, okay, that eigenvector of A will be the eigenvector of A inverse, will be the eigenvector of adjoint of A, will be the eigenvector of A raised to n, and will be the eigenvector of f of A. Okay, and that's why it is necessary to find the eigenvector of A itself, because that eigenvector of A will remain the eigenvector of all the derivatives of A. Here the meaning of derivative is which you can derive from the matrix A. Okay, and that's why if you are able to know what is the action of the matrix A, then that action will be for all its derivatives. Yeah, so all, it may be inverse, it may be adjoint, it may be polynomial, it may be any power. Okay, power means repetitive action. Okay, powers mean repetitive action. Okay, so that's why finding the eigenvectors of matrix A are very important. Yeah, and hence we need to understand this thing, that the eigenvector corresponding to lambda will be the eigenvector for all the powers and the scalar multiples of lambda. Okay, so that's what we need to know. Okay, now we have to think of the Cramer's rule. Okay, why we have to think of the Cramer's rule? Because whilst finding the eigenvector, we are going to solve the system of equations, linear equations particularly, and this system is homogeneous system. Yeah, this system is going to be homogeneous system. So we are going to solve the homogeneous system of linear equation. That is, our system will be always of this type. This is the type. Okay, so this is homogeneous always. Actually, we'll have the system a minus lambda I into x is equal to 0. Okay, and this is same as homogeneous linear equation. So we need to solve this, and while solving this system of linear equations, one rule which is very important, and that is Cramer's rule. Yeah, so we need to understand what is Cramer's rule. Yeah, so let us try to understand. Suppose let a1x b1y plus c1z is equal to 0, and a2x plus b2y plus c2z is equal to 0. These are the two equations. Okay, then the solution of above equations is given as. Okay, so what is the solution we have? So we have a solution x upon. Please be careful, these are the determinants. Okay, so determinant of b1, b2, c1, c2. This is equal to minus y. Determinant a1, a2, c1, c2. And this is equal to z. Okay, and here we have, this is a1, a2, b1, b2. Okay, so basically what we know is, we know ax plus by is equal to c. What is the equation of, what is the geometric figure that you get from this equation? What is the geometric figure related to this equation, or what this equation represent in geometry? Do you know what is? Yes, it represents a line. Okay, so this is a line in two-dimensional plane. Okay, so plane is having two dimensions. X and y are the independent variable. If I consider this as x and y are both independently, then this has the two dimensions. Okay, so this equation represents a line in two dimensions. Okay, and now if I add one more dimension, okay, so ax plus by plus cz equal to d. So what this will represent? This was two-dimension.
Three-dimensional
This is
line.
3 dimension. Okay, what is that? What this will represent?
A line in 3-dimensional.
A line in 2 dimension? No, we have a 3 dimension.
3-dimensional.
Yes, we are in 3 dimension now. So you have gone through the course Applied Mathematics 2, and you have gone through the multiple integrals. Okay, so what this equation represents? This represents a plane. Okay, what it represents? It represents a plane, okay, in 3 dimension. And if I put this d is equal to 0, okay, so ax plus by plus cz. So this ax plus by is equal to 0 is a line passing through origin. and hence this is equal to 0 is a plane passing through origin. Okay, so this will have this plane will have the cuts as x cuts will be d by a, y cut will be d by b, and z cut will be d by c. Okay, but this plane will pass through the origin. Okay, and hence we are having the equations of planes. So these are the two planes, okay, which are passing through the origin. And if I want to find out the intersection of these two planes which are passing through origin, then this is a line. So this is the equation of the line in 3 dimension. Okay, so this represent a line in 3 dimension, and that's why Cramer rule helps us to find the line in 3 dimension. Okay, so when we have two planes passing through the origin in 3 dimension, then their intersection can be calculated by using Cramer's rule. Okay, so here we are restricting ourselves to 2 by 2 matrices and 3 by 3 matrices. So we'll be in 3 dimension at the most, and in 3 dimension we are able to find the intersection of two planes passing through origin. Okay, because we have restricted that all the planes will be passing through origin. Okay, and hence we need to know the Cramer's rule. Okay, but the most important thing that we need to understand while using the Cramer's rule is these two equations must be different, must be distinct. Okay, so if these two equations are distinct, then only we are able to use the Cramer's rule. So for example, I'll write the two systems. Okay, so we can have x plus y plus z is equal to 0, 2x plus 2y plus 2z is equal to 0, x plus y plus z is equal to 0, 2x plus 3y plus 4z is equal to 0. So these are the two systems I have written here. So I have system 1 and I have system 2. Okay, now you have to tell me where the Cramer's rule is applicable and why. So can you tell me whether is the Cramer rule applicable to system 1? Is it applicable?
No, sir.
No. Why?
Because it's just multiple of first equation.
Correct. So these are not two distinct equations. It is the same equation. X plus y plus z is equal to 0. So it is x plus y plus z is equal to 0, which is the first equation. So here these are not two distinct equations, but these are the same equations. Okay, it's just the scalar multiple as you identified correctly. Okay, good. So here the Cramer's rule will not be applicable. What happens to this system?
It's applicable because both the equations are different.
Yes, here both the equations are different, so it is applicable. Absolutely right. Okay, so you got idea about the Cramer's rule, when and how it is applicable. Okay, so now I'll give you a shortcut to calculate the characteristic equation of a 3 by 3 matrix. Okay, so what I have is let A be a 3 by 3 matrix. Okay. Then characteristic equation of A is given as, okay, so what will be having lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equal to 0. Now what you know is, you know determinant of A, you know this term, this is going to be 1. Only we need to know what is S1 and S2. So we can have where S1 is equal to sum of diagonal elements of A. So what S1 is going to be? S1 is the sum of diagonal elements of A. And now what about S2? So S2 is also sum, but it is sum of minors of diagonal elements. So it is the sum of minors of diagonal elements. So how do we calculate minor? So you can get the minor from the determinant of A by deleting the row and column of that particular element. Okay. So for example, we have the matrix A. Okay. So this is matrix A, B, C, D, E, F, G, H, I. Okay, this is the matrix A, and I want to know minor of suppose D. Okay, so what we have to do is we have to find out the determinant of A. So it is A, B, C, D, E, F, and G, H, I. And now I want the minor of D. So what I have to do is I just have to omit the column of D and the row of D. So what will be the minor for D? It will be BC and HI. Okay. So from the determinant of A, what we have to do is we have to eliminate the row and column of this element. Okay. And then whatever the remaining determinant, that determinant is going to be the minor of this element. Okay. So this is how we can have. So if we think of minor of E. Okay, so A, B, C, D, E, F, and G, H, I. So can you tell me what I have to delete now?
Second row, second column.
Yes. So we have to delete the second row and second column. And what I will be having? I'll be having AC and GI. Okay, so this is going to be the minor. Okay, so this
Sir,
way, yes.
Sir, is this the shortcut or you mentioned the shortcut? I was there. I wasn't there, sir.
No, this is the shortcut. I am explaining. See, this S1, you have the sum of the diagonal elements. Okay, and S2. So I am talking about S2 now. So how to get S2? Because S2 is nothing but the minors of sum of minors of diagonal element. So how to
Yes,
get a
sir.
minor? Okay, how to
Yes,
get
sir.
a minor, that we are discussing. Okay, and now I want the minor of this element. So for this A, what will be the minor? This will be the minor for A. And then what will be for this E? Okay, so this element, this element, this element, and this element will be the minor for E. And what about this I? Okay, so this will be the minor for I. Okay, so what is S2? So S2 will be the minor E, F, H, I. Okay, plus the minor. Okay, you will be having A, C, G, I, and plus the minor. What you will be having? A, B, D, E. Okay, so this is going to be S2. So it is sum of minors of diagonal elements. So it is the sum of minor of A, minor of E, and minor of I. Okay, so this is minor of A, this is minor of E, and this is minor of I. Okay, so this way we are able to get the minor of A, minor of E, minor of I, and then if we add these three, then we'll have the S2. Okay, so this is the shortcut. Okay, so that's what we have. Yeah, so this is the shortcut.
So basically, instead of finding for all the elements,
Yes,
we'll do this
if you instead of solving the determinant of A minus lambda I, is
yeah, and then
zero.
finding adjoint,
Okay,
and then
you can directly go for this.
yes, sir.
But before that, what you have to do then? First find the determinant. Okay, then find
Yes, sir.
S1, then find S2. Okay, because once you find determinant, okay, so once you find this value, it will be easy to calculate the minors.
Yes, sir.
Yeah. Okay. So do you have any doubt up to 8?
No, sir.
Okay, because here in this lecture we discuss the properties of eigen values, the property of eigen vector, okay, and then we have discussed the Cramer's rule, which is very important. In one example, at least 2 times or 3 times we are going to use the Cramer's rule, so that's why it is very important, okay, and hence we need to be careful. So we must know this Cramer's rule very properly. Okay. So we got Cramer's rule, and then also we have discussed about the shortcut, how to get the characteristic equation for a 3 by 3 matrix. As I have told you that we are going to solve the problems based on 2 by 2 matrix and 3 by 3 matrix. So once you know for 2 by 2 and 3 by 3, you can extend this idea to any dimension. Okay, so you can go for programming and then find out this. Okay, so do you have any doubt now?
No, sir.
Shivam,
No, sir.
any doubt?
No, sir. No, sir.
Okay, Minal, any doubt?
No, sir.
Aditya,
No, sir.
Prachiti,
No, sir, no doubt.
okay, all of you got this idea?
Yes.
Have you understood
Yes,
this
sir.
idea?
Yes, sir.
Yes, that's
Yes, sir.
good. Okay.